My name is Joseph Hoff. I'm a licensed fire protection engineer practicing in the light safety industry for 30 years. I'm here to help spread information and education on the subject of fire-rated ducts and enclosures, because over that 30-year career, unfortunately, I've seen a lot of mistakes. I've seen a lot of the solutions that evolved over that time, and I can help you avoid the pitfalls that I experienced over that career. Quite frankly, the reason for my educational mission is that as a special inspector writing a rational analysis report for a building or performing the special inspections myself over that period, I was reconciling the problems one building at a time, usually very, very late stage, to the great frustration of many people on the construction team, and there had to be a better way. So this course gives me the opportunity to share those experiences so that there's many more eyes on the problem, and we can start getting it right more often than wrong. And I think you'll agree that we have a problem in the industry of fire-rated duct products. And the solution is not that hard, but it is harder than you might possibly imagine. So with that being said, we're focusing on the criteria in the state of Michigan codes as referenced. We're going to touch on building code, mechanical code, life safety code, and some of the NFPA reference standards therein. We will not be talking too much about grease duct, mostly in the sense of how we distinguish grease duct from the other fire-rated ventilation duct applications that are in the code. The reason for this is that the grease duct is tested to different pest standards, and they are largely followed well within the wild, as I like to put it, and that is in contrast to the fire-rated ventilation ducts for most other applications that are that we find code paths to fire resistance, because the test standards are different and the implementation is different. And we're going to find that that's where much of the confusion comes from, because the fire-rated ventilation duct designs that are supposed to be being used are coming from, they were either born here in the US market from the grease duct industry, or they were born over in the UK or British industries where their code systems are very different, and those differences matter. So we are talking about those fire-rated duct products that are applied as a substitute for fire resistance that's in the code. And that might come from a requirement that stipulates the need for a fire damper in an HVAC system, or the need for a shaft with fire resistance to protect an HVAC system. So we're dealing mostly with life safety applications, and that's where we're going to find most of the criteria, the code paths, coming back to the fire resistance that's prescriptively called out in the code. We are talking only about the ductwork that is in the code specified for that fire resistance. I once was accused at a presentation, I think it was up in the Northeast, where someone somehow got the impression that I was suggesting that all of the HVAC ductwork in the building needed to be fire rated. In no way, shape, or form are we talking about all of the HVAC ductwork in the building. There are specific code paths where specific ductwork is identified in the code. That's the ductwork we're going to be talking about. You should be able to apply what you're learning here to a number of different common applications called out in the code for these kinds of fire resistance and the protection of the ductwork systems, and often the fans, power, and controls associated with these systems. We'll talk about all of that as well. Some of the most common and simple systems are stairwell and elevator shaft pressurization, when those ductwork systems are within the building envelope. Certainly, if there are inline fans in the building, they need to be in dedicated, we'll talk about that, rooms with fire resistance equal to the shafts in question. And we can see that there are products out there that are fire rated for the enclosure of those fans when there cannot be easily programmed into the space plan a dedicated fire rated room for that fan. We have common smoke control systems using the 4 different methods: pressurization, exhaust, airflow. And we're going to talk a little bit, because it has context when we talk about the passive smoke control criteria in section 909 of the building code, and the parallel provisions within section 513 of the mechanical code. So subduct exhaust systems actually are a pretty important life safety system. We're going to talk about that. It's often overlooked, some of the common mistakes that can interfere with those, and they are required to be configured very, very specifically so that they are able to function during a fire. And we're going to talk about the common mistakes and how to avoid that. Utility stack vaults, when we deal with, if you're dealing with high-rise buildings, very, very tall structures where they're going to start, taking advantage of utility grade voltage to keep the electrical conductors smaller, we're going to talk about the trade-offs that happen in terms of fire resistance up within the building, and those trigger ventilation requirements that may exceed the 2-hour threshold. That is a very, very important threshold when it comes to fire resistance for HVAC systems. Hazardous exhaust is another one. So if you work in buildings with laboratories, common universities, production facilities for manufacturing, we're going to see that there are some that get up to 3-hour fire resistance ratings there as well. Ventilation riser offsets, the floor plate changes, or simply the architect desires some freedom of design. And so the riser is over here on one floor plate, and on the next floor plate above or below, it shifts on the plan. We have to get horizontally from one to the other, and we have to often maintain our fire resistance rating of that offset. We'll talk about when you do, when you don't, and what the difference is. And of course, there are now products that actually are legitimately replacing the shaft itself with a fire rated duct product. And the reason I'm going to home in here on the criteria that says 4 or more stories is because that's what triggers that 2-hour fire resistance rating. Below that, it's only 1 hour, and if you're only penetrating one floor, of course, you can use a fire damper. That 2-hour threshold is extremely important. We're going to talk about why. So those are the things you need to look for, those threshold issues, and you're going to find the criteria and the code paths peppered throughout the presentation. So there's nothing I'm going to talk about that I'm not going to give you the citation that you need to use to go find the criteria in the exact language of the code, because I want you to validate everything to your satisfaction, and to cite that if you're involved in the design, the inspection, or the approval of the design. These are the citations that will come in handy, and this is a reference tool for you, hopefully, moving down the line. And we're going to talk about some concepts that are fundamental fire resistance concepts that aren't often commonly, if you're doing mechanical inspections or mechanical plans review, you're not necessarily playing around in section, chapter 7 of the building code too much. And yet that's where most of this criteria is going to come to play. And it's really important to recognize that it is so much more than just simple, well, we'll just put in a SMACNA-based ventilation system according to the mechanical code. And there's some things we might need to do to it. And anything could be further from the truth once we get into the weeds. And we're going to get fairly deep into the weeds, because that's what it takes to get a true understanding of these issues. So symmetry is one of those fire resistance concepts. And we find that all of the code paths that we're going to talk about related to fire rated duct systems, other than grease duct, it might be 1 step, it might be 2 steps, it might be 5 steps to go from one code reference to its code reference to the next. But you're going to find that they all land at 703.2.1, which is a pivotal paragraph, because this is the paragraph that says you must test the assembly to the fire resistance test standard. And we're going to make that citation at the appropriate juncture. And we're going to talk about orientation in the context of the duct moving through the building horizontally or vertically. And that means it's going to be parallel to the assemblies, the other fire resistance rated assemblies in the building that are moving, being built in the building in the horizontal and vertical orientation. So as we move through those fire barriers and those fire rated floor ceiling assemblies and even the roof assembly, we're going to need to be cognizant of the fact that orientation matters, because continuity support, as the phrase is applied in 707 and 711 of the code, are mandatory for all fire resistance rated systems. And that includes fire rated duct systems. We'll talk about why that matters. Generally speaking, every floor assembly, wall assembly, shaft assembly, these are all defining compartments. Compartment equals passive fire resistance, and it is the backstop to all of the active protection that's in the code. It is the minimum requirement, and it's there for very, very good reasons. And we'll talk about why those reasons exist. And I'm going to start with one of the simplest smoke control systems that we're probably going to come across. At least most people think of it that way. And that's a stairwell pressurization system. So we see that we oftentimes have a building tall enough for the roof access to the shaft is simply not readily available for the equipment involved. We can't do the simplest form of injection of the air into that shaft to pressurize it. It is the most common solution to the smoke-proof enclosure criteria in the code. So what do we do when we need to get the air moving through the building to get to the stair shaft at one or more levels to provide a nice even pressure profile that's going to allow the doors to work and yet effectively control the fire products from entering the stairwells? This is one of the most sacrosanct shafts in the building. So getting this right is really important and surprisingly difficult, because what we're looking at right here is the fire scenario that most people think of when they think we need to protect the stair. So we have an HVAC system that's dedicated to protecting this exit stairwell. And what we unfortunately see is what I call the most common design to failure scenario that's out there. And I say design to failure because they used one of the more common fire rated duct configurations, and in so doing, they needed to provide a fire damper at the penetration of the stair shaft fire barrier. And this is a classic case of more is not better. What we have here is a fire damper which is going to close, and when it closes, it interrupts our smoke control system. And this is actually prohibited by the code. And we are very, very, very commonly making a mistake that renders a whole lot of equipment and ductwork inoperable at exactly the time that it's needed most, because the simplest component of the system did exactly what it was supposed to. And actually, the code instructs us very, very, very clearly in section 909 to envision all of the probable fire scenarios. And so there's a lot of myths out there about which fire scenarios you need to abide by. And I assure you, as someone who has spent my 30-year career immersed in fire science, it tells you they know how the fire is going to attack a building and how it's going to move through the building, and that it'll never do this and it'll never do that. Their crystal ball is better than anyone's I found yet. And I talked to a very, very select group of very, very, very smart people who have put a lot of thought, energy, and there is nobody who can tell you how a fire will attack a building. And I assure you that it will find a way. The weakest link is what will be attacked, and the fire will move in very, very, very strange ways. And this is the reason that the fire resistance criteria and the code related to duct systems, which are going to be demanded to perform during the fire and or penetrating the passive fire resistance barriers to contain the fire to the compartment of origin, are going to be challenged. And the weakest link will be the thing that fails. And when our life safety designs for these systems and the mistakes that are commonly made are the source of the fire moving from one compartment to the next when it's not supposed to, it's just about the worst possible outcome that you can imagine. Designing to failure needs to stop. And we need to do that. The first step is to avoid wishful thinking. My mentor drilled this into us back in my early days. Wishful thinking is what gets you to those convenient fire scenarios instead of considering all of the fire scenarios that we're supposed to. And wishful thinking ignores fundamental facts about fire resistance. For example, that fire damper, very, very simple device. Much like a sprinkler head, it's usually a thermal link or a thermally activated device. It's going to close when we reach that threshold temperature. But when we're dealing with life safety systems, we know that we want it to work during the fire. And if you're familiar with the fire resistance test standard, that is our benchmark, ASTM E119, or its counterpart UL263, we know that the passing temperature on the unexposed side is around 400 degrees. It's a threshold above ambient, assuming ambient is around 70, 75 degrees in the test lab that day. They're going to be looking for a threshold temperature of around 400 degrees on the unexposed side as part of the pass-fail criteria. There is no such thing as a listed damper that can be put inside of a fire-rated life safety duct that will not operate well below that threshold. So if we're looking for a duct that can survive this fire scenario, the standard time temperature, it's going to get, again, at 2 hours is a really important threshold. We're looking at around 2,000 degrees. And on the inside of on the other side of the unexposed side, that's going to be around 400 degrees if the barrier is working correctly. So we can't have something on that unexposed side, on the inside, that we need to be moving air during the fire that's going to close and render the system non-functional. And we'll talk about what we're supposed to do rather than do that. What's important is that what we do as an alternative to that fire damper needs to provide the equivalent alternative protection to what the fire damper was going to do. We're going to talk about equivalent and alternative are terms that are going to come up a lot, and there's a reason for that. We're going to need to understand some jargon. In the duct industry, fire-rated duct industry, there are two different test standards, and they use different jargon to describe their test specimens. And those are things we need to look for in the product data, because if we don't understand that jargon and we aren't looking for the right jargon, we can't possibly be getting it right. So if you're not familiar with the terms duct A and duct B, when we're talking about the ISO 6944 test standard, if you're not familiar with condition A, B, C, and D, when we're talking about the ASTM E2816 test standard, then you can't possibly be getting this right, because they describe how the test specimen was tested. Was it tested on just one side, or was it tested on both sides? Because the code tells us very specifically which of those things we're supposed to be doing. And one of the dirty little secrets of the fire-rated duct industry is that most products have not been tested completely. It is one of the rare test standards where the test laboratories will allow what they call provisional listings. We'll see what a provisional listing means and the dangers of not vetting which test specimens were tested when we are applying designs that are based on provisional testing. Because when we take that damper out, which we want to, we don't just want to, the code demands that we take that damper out if it's going to interfere with our smoke control system. When we take it out, we need to ensure that we're providing equivalent protection to the compartments where we're not providing the opening protective. And that means considering that specific design scenario that comes first to mind when we're needing to get that air safely to the stair shaft. And this could be any compartment using the pressurization method or the exhaust method. It's just the stair pressurization system that has the most confusion. And we'll talk about that as well. So when we omit that damper, we need to use what they call in the fire-rated duct industry, most common designs out there are going to be ISO tested designs. And ISO 6944 describes the test specimen that allows you to omit that damper as duct B. We're going to talk about exactly what duct B means. But before we do that, I need to, let's benchmark how that test specimen compares to what's in the code, because you're not going to find in the code duct A or duct B. They're just going to describe the fire resistance. The test specimen tells you what they tested and whether it meets the fire resistance described in the code. But what the code conventionally, prescriptively describes is a code path back through Chapter 7 to 703.2.1. And depending on the orientation of the assembly that is described as needing to be fire rated, it's going to be either in the horizontal orientation or the vertical orientation. And when we do that, we are absolutely changing the structural stresses on the backbone of these assemblies. And it is, I assure you, much harder at fire temperatures to achieve the same fire resistance performance out of horizontal assemblies rather than vertical assemblies. And we're going to talk about that and why. But this is this is my favorite unicorn. And I call it a unicorn because it is a design that I see on architectural drawings all the time. And I understand how we get there, but we need to stop, because this is actually a deviation from the actual design that's referenced at the bottom of the page. Okay, what happened here is form over function caused the designer to make a fundamental mistake. They have a horizontal duct that needs a fire resistance rating. It needs to get from an outside air louver through the building to a fan, from the fan to its endpoint, whether it's a stair pressurization shaft, a pressurized stair, or an elevator shaft that's being pressurized, what have you. That duct, if it needs to be 2-hour rated, has some serious challenges to get to that 2-hour rating. And this U-shaped box that we've all, if you've been in the wild doing inspections, if you've been reviewing plans, I'm really surprised if you haven't seen the U-shaped box, is what I call it. And unfortunately, the U-shaped box does not exist in any design guide from UL, Intertech Laboratories, any IAS certified test laboratory. It does not exist in the Gypsum Association design guide. There is no source that actually has a listed or approved U-shaped configuration. And the reason is very simple. Light gauge wall framing tested as a wall assembly sits in the furnace on the slab, goes up to the top, gets pinned to the bottom slab, gets pinned to the top slab. That light gauge framing is in simple compression, which does actually pretty darn good at fire temperatures. And when we take those assemblies that were designed under those constraints, tested under those constraints, that's how we're allowed to use them. That's what the code says. You're allowed to use it the way it was tested. So you can't just get rid of any of that design that's been listed and approved or promulgated by the online directory for the test laboratory or Gypsum Association or what have you. You have to use it the way the design, the way it was tested and the way it is in the design. When you deviate from that design, you're no longer dealing with test results. You're no longer dealing with calculations. You're dealing with conjecture. Somebody's guessing. And that is not what the code says. So what we're going to see is that when we have a horizontal duct and we want to use conventional construction to protect it, we actually have some serious limitations. On the right-hand side here, you see the UL listed design for a horizontal drywall assembly. Okay, this would have a duct above it with a 2-hour slab above that. So this would get installed below the duct, which is pinned up against the 2-hour slab, sandwiching between two fire-rated assemblies. We have a fire-rated duct. Unfortunately, this is the one and only 2-hour design for a drywall horizontal assembly in the entire UL directory. And it is not a U-shaped box. It demands a 2-hour wall on each side of that horizontal assembly, and that 2-hour wall must rest on the floor and go up to the slab above, and it creates an H, if you will, It provides the continuity support that's required by 707.5. Remember, orientation matters. That continuity support concept says I must have the entire assembly supported, structurally supported by fire resistance elements equal or greater than the assembly's demands. So if I have a duct system that needs to be 2-hour fire rated according to the code path, I need to have continuity construction 2 or more hours connected to a wall, connected to a floor, connected to a beam, a girder, everything that it connects to structurally back to the foundation of the building must be equal or greater than 2 hours. And when the design that was tested by the test lab says it must be supported by a 2-hour wall on each side, you can't just get rid of the walls. And the reason for that is pretty simple, because the walls were tested under that simple compression where they retain most of that compressive strength residually at fire temperatures. But when we lop off the bottom of those walls and we create these U-shaped boxes, what we're doing is taking the same lightweight framing and putting it under tension. And what we know about tension, steel has very, very well-known properties. We know a lot about steel at high temperatures. One of the most studied materials in terms of fire exposure. And what we find is that for those assemblies to stay up in the air, protecting that horizontal duct, we need a 2-hour wall to hold the box up. So what's actually been tested and approved for use in the wild is actually an L-shaped assembly that's constructed around a duct that's been tucked up in the corner of a 2-hour wall and a 2-hour floor slab. That's as good as it gets when you start using drywall. If you've seen drywall different than an L-shaped box tucked up and supported by proper continuity support by a 2-hour wall that follows the duct path all the way through the building, then you are looking at something that is going to be down on the floor once it actually gets hot, because at 70 degrees, it may well stay up there. But ambient is not what we're aiming for. We're aiming for it to stay up there and protect that duct at 2000 degrees for 2 hours. And if it's not this design, then it doesn't exist for drywall. And so we can see why a lot of people go to fire-rated ventilation duct, because the fire-rated ventilation duct doesn't have those constraints. Its continuity support is equal, but provides more freedom. So we don't need that 2-hour wall following along the fire-rated duct path, but we have other things that we need to pay attention to that are often overlooked. So what are those drywall assemblies doing? This is what they're doing. They're providing the prescriptively described fire resistance. They're protecting fire exposure from either side, because that's what we're required to do as a minimum. And they're doing it for the horizontal assembly, and they're doing it for the vertical assembly. And we can already see that horizontal is harder to do than vertical, because when we just look at this, we can see that it's a heavier gauge, heavier channel, deeper channel, steel backbone to the horizontal part of this assembly than the vertical part. And we can see it takes an extra layer of drywall on the horizontal part versus the vertical part to get to that same 2 hours. Horizontal is harder. It's not just harder with drywall fire-rated assemblies, it's also harder for fire-rated duct assemblies when we start moving through the building horizontally versus vertically. We need to pay attention to that because we have to use it the way it was tested, right? How many times have you seen a drywall assembly where they took the vertical wall design and just brought it down and turned it and ran underneath the duct horizontally? They didn't even do the horizontal up build that is minimally required. They took a wall design that was tested vertically and they turned it horizontally. It's not going to work. I can't stress enough here. These are all life safety applications. All of these systems need to work to protect the property, to protect the occupants. If we don't give the first responders the chance that they're expected to have to do their structural firefighting through protected means of access to the building, we are fundamentally failing. And anything less than what is fire rated by testing, by design, is just wrapping paper made to look like it's fire rated. And that's worse than doing nothing at all, because that has people coming into the building, whether it's the occupants, whether it's the structural fire response. These people think when they look up that they have what they're supposed to have in the way of protection. The best analogy I can make is like those newspaper articles we see when occasionally you'll find some inspector who popped his head above a ceiling doing an inspection and he found no piping behind the sprinkler head. The contractor, for whatever reason, decided that it was going to be too much work. I don't know whether he ran out of materials, the schedule got up on him, but for whatever reason, he made a really, really poor decision. He decided that the appearance of a fully sprinklered building was going to be sufficient. And where he got caught out without the right piping to the right place, he just screwed a head into the tile and walked away with his fingers crossed, hoping that nobody was going to notice. And it surely dawned on him that that sprinkler wasn't going to work if there was ever a fire, and yet he didn't care. So we have to guard against, this is the importance of the inspection side of enforcement. This is the importance of due diligence and construction administration on the design team during the build process, because we don't always have good actors out there putting in these life safety systems. But I assure you, if we put in less than the fire rated design for the protection of the life safety HVAC systems in a building, we're doing exactly the same thing. It's settling for the mere appearance of fire resistance, which is worse than nothing at all. We're going to talk about a lot of the things that are done in the fire rated duct industry that literally are worse than doing nothing at all. Because what it takes when you get into the designs to provide equivalent fire resistance to those drywall assemblies that are prescribed by the code, we're going to see something very different than probably what you're used to seeing. I don't know how many of you have seen minimum 2-inch pressure class SMACNA duct with one layer of some kind of fire product on it. And somebody's telling you that that's fire rated for 2 hours. And I'm here to tell you there were a whole bunch of mistakes made along the way to that concept. What you're looking at is multiple layers of a fire rated product around a duct that could only be best described as SMACNA on steroids, and you just got to the equivalent fire resistance of the drywall assemblies. And if this is not what you're seeing out in the field, you're not getting 2-hour fire resistance. This is what the fire rated duct system must do to be equivalent to those drywall assemblies. When we take the build construction away, if we're not going to have shaft construction, then we need to have the equivalent fire resistance. And that means it needs to be protected from all the same fire scenarios, the same continuity support. Then we have equivalent fire rated duct product on our job. And so we need to validate that it can move the air. We need to validate that it's going to be there. And so that burden falls on the people who not necessarily are immersed in checking fire resistance concepts. So we need to understand symmetry. We need to understand continuity, because it was a subtle change. But the difference between equivalent and not equivalent is exactly the problem with the industry. Because right now, more than 90% of the product designs that you will find in the UL directory, the Intertech Laboratory directory, any IAS certified test lab in the US market is the second configuration, the one that is not equivalent. It has only been partially tested. It is what they call duct A instead of duct B. Duct B is fully tested, fire inside, fire outside, both sides. Using the lower of the two, the hourly rating is the assembly rating. That's what the code tells us to do. If we only test part of it, we didn't do our jobs. And if nobody's checking, then it slips through the crack. And I cannot tell you how many jobs I have walked into in my 30-year career where it almost slipped through the cracks. And it brings me no pleasure as the smoke control special inspector to walk into a building a week before everybody thinks they're going to have their TCO, and I am in the process of sliding all of that hard work that they did on the T&B back across the table without even turning the first page. Because there's no point to my checking those T&B results. It doesn't matter if the ductwork is pressurizing the stairwell adequately. There's nothing for me to check because I can tell from the floor where I'm standing that it's not a 2-hour fire rated duct assembly that I'm looking at. And the code says that a 2-hour fire rated duct system needs to serve that stairwell. And I know that that means they need to take the whole thing down and put up one that is 2-hour rated. And this is another sad truth. There is nothing you can do to a deficient system to retroactively make it fire rated. We're going to talk about why that's true. Because if you don't know what the design is, you can't possibly amend it after the fact and get it to a place of fire rating. Because the backbone matters as much as the skin. We're going to talk about the backbone, the structural backbone. In the world of fire rated duct systems, the steel duct, its flanges, its seams, and its external and internal reinforcement are the backbone of the assembly. They are what hold it up in the air, just like the steel stud holds that drywall up. But the drywall is no more fire rated without the stud to which it's attached and the ability of that stud to hold the wall up for 2 hours than a fire rated duct system is capable of being called fire rated because of what happens to be on the outside if what's underneath can't support it for 2 hours. And that's exactly what happens when we don't know what we're building from the very, very, very get-go. Because there's no such thing in fire duct design land where the assembly is going to be minimum SMACNA construction without locking flanges, without locking seams, without external reinforcement, except for extremely small duct sizes. And this idea that you could have this minimum SMACNA construction with one layer of something on it and somehow get to 2-hour fire resistance doesn't even pass common sense. We'll talk about that during the brief moment that we talk about grease duct. That's my sanity check, and I don't understand how we step over that basic sanity check to get to duct A for these life safety applications that are so much harder than grease duct. So unfortunately, flip through the directory if you ever have time to kill. Open up the UL online directory, click on fire rated duct. I think it's 30 odd, slightly less than 40 designs that you'll find in there. And 9 out of 10 of them are going to look like this. And unfortunately, that duct A, it seems innocuous over there because it says fire rated, it says 2 hours. That's what I want. I need the U shape or I need the L shape. That's what I want. You know. But if you don't know that that duct A at the top of the page in that very, very first line, the very first row, you should be having red alarm bells go off in your head when you see duct A without duct B, because it tells you that this product configuration was only provisionally tested. And once you know what the provisional limits of what was tested, you realize that this has no legitimate use whatsoever in the US-based code system. It's a test specimen born in Europe and the UK, where they have a totally different approach to fire-rated ducts, completely different than ours. Their concepts of fire resistance bear no resemblance to ours. And the fact is, in the US code system, duct A and duct B are merely test specimens from a test standard that tell us whether or not they did their testing on both sides and whether they used appropriately the lower of the two results, which is what we need to do according to our building code. So you need to know that duct A and duct B are very, very different. You need to know that they don't always test duct B, that they can get listing cards. You just saw one where the only thing they tested was duct A, and they will use it for all purposes under the sun if you let them. And we are not just cutting quarters esoterically. I'm going to show you the pictures of what happens when we use the wrong ductwork and we have real fire exposures. We're going to talk through the scenarios, real world fire scenarios, where those same problems that we see in those photographs are going to happen if we don't fix it before it gets approved. because we have to test fire inside and fire outside to meet the symmetry testing requirements of the building code. And we have to test it vertically and we have to test it horizontally if both orientations of ductwork are going to flow through our building. That's a completely tested product. So what do I mean when I say the struggle is real? You know, these aren't just theoretical problems. Here's one of the many, many, many photographs I've taken over my 30-year career, and it's almost a case study in how you could do anything and everything wrong when it comes to protecting the most sacrosanct shaft in the building. This is going to a stairwell. It's a stairwell pressurization system. Inside the drywall box is a stair pressurization fan. We see an access panel in the bottom. We see a plenum box that feeds the intake of the fan that's connected to a louver on the left there. And we see the discharge coming past the smoke detector, which we're supposed to see. And then we see the ductwork continuing on to the shaft. Unfortunately, there is nothing fire rated about what we're looking at. We can break it down, but the strap that you see connecting it to the wall, I assure you, for other than a duct that's smaller than 16 inches, there is no gripple wire in fire duct land, and there is no strap in fire duct land other than for very, very small ducts. The duct on your right is about 2 feet by 2 feet. The plenum box is the width of equals the width of the fan enclosure. I use that term loosely. We'll talk about why. The plenum box is over 4 feet wide and well over 6 feet deep. It's approaching 8 feet deep. So once you know the constraints on drywall, once you know the constraints on the insulation class of products, you realize that that plenum box is well larger than the kind that allow a strap support. So that strap support means one end of this plenum box is going to fall away from the wall as soon as it's exposed to fire, very, very, very shortly after. In no way, shape, or form is that going to get close to 2 hours. We also realize that the technical manuals for every product in this class does not allow the bearer to go underneath the insulation. So we see that happening on the plenum box as well as the duct. We see if it wasn't off screen, we'd see the bearer was also wrapped. We don't see bands on the plenum box, which is really strange because we see bands over there on the duct on the right, yet it's the same fire resistance product using the same designs. Why would we have the bands on the smaller duct and not on the right where we see the plenum box? So the only thing holding this fire rated assembly together is aluminum adhesive tape. This is a bad side imitation, mere wrapping paper. This is made to look fire rated, but and is very dangerous because of that, because this is not even close to the technical manual for this product. Okay. The truth is, on the right, we see a 2x2 duct, which may well be okay to use steel bands at the prescribed spacing. The problem with the duct on the right is that they're using the most common joining method. Every seam has a collar around it. There's like 4 different ways they can overlap the seams correctly. And the collar method is one of them. But every loose end requires a band. And the collar is the only one that has 2 loose ends underneath of it, which means it needs 2 bands, one on each side of the collar, so that each piece underneath of that collar is properly secured. We only see 1 band. I'm going to show you what happens when you only put 1 band on a collar joint on an insulation class product. The fact that they skip the bands altogether for the plenum box is a complete mystery, because as it gets bigger, you actually need to start pinning 1 or more sides as well as provide bands, so it becomes more stringent, not less stringent as the duct or the plenum size increases. We also see that I can see from the floor that there is no proper fire stop at the penetrations of the drywall box. The fire stop matters as much as the duct. If the duct is going through something fire rated, it doesn't matter if the duct stays there for the 2 hours if the fire goes right past it and through the joint to the other side of the compartment. We fundamentally failed. Every fire rated duct is tested with companion fire stops. There's no mystery here. The fire stops matter as much as the duct. Match them up, follow the entire assembly. We also see that that duct smoke detector doesn't have a 2-hour cover. I want to see the duct detector. I need the duct detector, but I can't just cut away the fire rated assembly to put it on. If I can see accessories, actuators, duct sensors, pressure sensors, duct smoke detectors, anything that we're carving away to attach to the duct needs to be protected. We violated the fire resistance. We need to put a 2-hour cover on that. And the 2-hour covers are not just more insulation slapped over the accessory. It needs to be accessible for service and maintenance. It needs to be within its operable temperatures. And that means they need to provide an access panel around a standoff cover. We're going to show you what is actually in the technical manuals that are required to accomplish this. And when we look at the drywall, we realize that the 2-hour wall, if the exterior wall is 2-hour rated, we would have to check that. But even if it were, that span is more than 5 feet. So we know we are past the limit for a cantilevered single-sided support. They would need to have another wall at the other end, even if it was only 5 feet wide, to hold that end of the box up, right? That's the continuity support required by the design. If we don't put it in, it's not going to stay there during the fire exposure. The contrast isn't great, but if we look in that opening, you should be able to see that there is a lightweight wall stud in the horizontal orientation. That's not going to work in the horizontal orientation. They also did not put in a shaft liner, and they certainly didn't put 2 layers of drywall on. Again, you know, drywall on some lightweight framing is not fire rated. It needs to follow the designs for a compartment that can be supported in the air, and that means 3 layers of drywall minimally on the bottom, a shaft liner, and a heavy gauge, thick gauge, deep channel stud, CH stud on the bottom panel, 2 layers of drywall with a shaft liner on the sides, and those can use wall studs if they stay within the 48-inch maximum depth limit for those designs. If you can't stay inside those designs like they did for this box because the box is too long, then you need to do what? You need to do something different than drywall. So we need to understand the drywall industry jargon. We need to understand the fire rated duct industry jargon. We need to know the difference between these applications. And within all of that, we have the opportunity to change what I call code by osmosis. And it's a term I acquired from an inspector once who said, you know, you have a journeyman who teaches an apprentice, and he becomes a journeyman, and then he teaches an apprentice. And the next thing you know, you have these conventional wisdoms that are propagated for generations. And all it takes is for one person at the beginning of that chain to miss something like this duct A, duct B thing when it first comes out, for that mistake to get propagated for years and years and years. And the consequence is that we don't have compartmentation. We have compromised everything from penetrations to entire runs of what are supposed to be shaft equivalent duct work. We omit dampers that we've not got equivalent protection for, alternative protection for, and so we are compromising the safety of the occupants, the expectations of performance for the first responders, and most certainly have not provided the property protection due the owner for a proper code complying structure. So the first thing I'm going to ask you is recognize that when we take the built assembly away from a bare duct, as described by the construction and the code, and we substitute a fire rated duct for that entirety, we now have an assembly that has been tested as an assembly that is the duct and the fire rated assembly all built into one. And it is non-symmetrical like those shaft walls, different materials being attacked in a different order. And that means we need to pay attention to testing both sides and using the lower of the 2 results. And then and only then do we have symmetry and continuity protection for a full compartment. And the way to do that is to verify through the listing card that the duct has duct B. Verify that it was actually tested in the orientation that you're seeing it, because yes, there are people who only test it in the vertical orientation and they don't test the horizontal orientation for the same configuration. That means that design cannot be used in the horizontal orientation because we know what? It's really hard to go horizontal and maintain the same hourly rating. If they skipped it, they're only allowed to use that configuration in the vertical orientation. And so there's all kinds of designs where it's been tested vertically and it changes once it goes horizontally. And once it goes horizontally, we need to switch to the horizontal configuration because the entire assembly is tested and it's allowed to be used in the orientation to which it was tested. We can't take vertical assemblies and use them horizontally any more than we can take assemblies that were only tested on one side and substitute them for built construction that was properly tested on both sides. Okay? Those are the first pitfalls, and that's the jargon that we're going to need to pay attention to moving forward. And it's all because we have some very, very simple concepts. You're welcome to go back and investigate it. I'm going to draw some parallels here to the wet side of mechanical inspection. When you're looking at fire protection systems, you're looking at sprinklers, you're looking at standpipes, you're looking at the piping and distribution of those systems, you notice something. You know, at the branch line level, it's a 1-inch pipe with some water in it. Why are we using all thread rod with cracked concrete anchors and clevis clamps closely spaced together? Is that way overkill or what? To hold that up in the air. The cold water pipe right next to it, the hot water pipe right next to it, not being supported like that. And the reason is that 2000 degrees, when that sprinkler system still needs to be there, and that standpipe still needs to be there, still needs to be working for those 2 hours, that's what the residual strength, tensile strength is of the steel support system. That clevis clamp, that all thread rod, that cracked concrete anchor, all of those things are designed down to their residual strength at 2000 degrees. And so it goes with fire rated duct. All of these duct systems have a steel backbone and an exposed steel hanging system. And this is why I say there's no such thing as minimum SMACNA in fire duct land, because minimum SMACNA is designed to hold duct up at 70 degrees ambient, plus or minus creature comfort temperatures. Fire rated duct systems need to stay up there at 2000 degrees for hours at a time. And the sad truth is, at that 2 hour threshold, most manufacturers chose not to test the duct for 2 hours, duct B. They tested it 2 hours, at 1 hour. They tested duct A 1 hour, duct B 1 hour. They went to 2 hours, they tested 2 hour duct A, and then suddenly, for some strange reason, they stopped testing 2 hour duct B. I can't say why. I just know from the testing that I've seen done that it's really hard to pass that test. And let's face it, if they're getting away with selling duct A for things that should be duct B, and they're not being held accountable for making that compromised product design on the street in applications where it will fail, it will not meet the intended fire exposures, they're likely to keep going. Why do I say that? That I can say, because when I talk to contractors and I talk to designers, I find about a 50-50 split of the people who I show these pictures to, they get it. At the end of the presentation, they'll say, oh, you know what, I get it. I understand what you're saying. Unfortunately, 1 out of 2, the very next thing out of their mouth is, but if I do what you're telling me to do, it's going to be more expensive. And I'm not going to get the job. And the other guy's going to get the job because he's not doing it. So 1 out of 2 doesn't believe that it's in his financial interests to do it correctly because he thinks someone else won't. And because he thinks someone else won't, and because he doesn't believe, based on his experience, that he will get caught doing it incorrectly, even though he knows the correct way to do it, he's going to keep doing it until somebody makes me. That's where we are. I've been on my mission now with this fire rated duct industry to fix what I think is one of the most broken industries in fire protection. And I'm at this place where half the people that I educate tell me they're not going to do it until someone makes them. So for example, the architects who see this design and I tell them, the fine print down here says you must have a structural engineer design the anchoring system, because the wall design that has been scavenged by the Gypsum Association for this design says that. And it says that because the typical wall only has anchors designed for pinning to keep the wall from tipping over during the fire. They're not bearing a load. They're not bearing even half a load. This is cantilevered. Remember, we have a 2-hour wall on the left. The right side is cantilevered, which is where the stress on the horizontal is coming from, torsion, shear, and tension on the bottom of those studs. And then on the right-hand side, it's completely under tension. It's bearing the load, half the load of that assembly. And what you find from a competent structural engineer who's told to design that for the residual strength at 2,000 degrees is that it takes 600-pound pull-out and 350-pound shear. Somebody better check that, because your average drywall contractor is not going to install an anchoring system for lightweight steel framing that's 600-pound pull-out and 350-pound shear. I posit to you that if it's not on the design, if it is not in the design documents, the structural calculations and the explicit anchoring system to be provided, if that is punted to the construction team and left to the average drywall contractor, you're not going to get an anchoring system that's going to hold even the L-shaped box up for 2 hours, okay? The span limit is 5 feet 4 inches internal dimension, and the depth is 48 inches inclusive of the assembly itself. So that in reality results in a maximum duct dimension once you account for a hanging system to hold it up and the little bit of room that takes. The drywall solution caps out, if it has a 2-hour wall, for continuity support on one side at a maximum depth of duct depth of about 36 inches and a maximum duct width of about 60 inches. If the duct's bigger than that, drywall is not an option with just one wall. Now we need to put in a wall on both sides. Remember that UL design? That UL design with a wall on both sides of the horizontal panel can go wider. They can go up to about 14 feet if they use really deep CH studs. And then you have the architects who just simply do whatever they please. This, when I asked the architect, where did you get this U-shaped box? It's very interesting. His answer was, I think I saw something that looked like this, so I just drew it up. So he just literally made it up. No UL design numbers, no design guide, no directory. Didn't use the performance-based tables that are in the building code under 721 or 722. We'll talk about why he didn't. He just made it up. We don't get to just make up fire-rated assemblies. Okay. Here's another common misconception in the drywall world, is that we have corridor designs that are used for enclosure of the duct system. This is a lay-in ceiling. This is not a lay-in ceiling. This is a false ceiling, right? And it looks like an H design, but if you look very, very closely, they don't have the shaft liner protecting the duct area to the exit passageway. What are we protecting here? In this case, we're protecting the duct from the exit passageway, but we're not protecting the exit passageway from what's above the ceiling. I think we missed something. There's nothing in the code that talks about furred wall construction as protecting anything that needs to be fire rated. One-sided protection is reserved for exterior walls only, and only then when they have a lot line setback that's complying with no fire exposures, no abutments, no unprotected openings that violate the very rare exception for exterior walls to be fire rated from the inside only. That's the only thing that approximate what a furred wall might impart in terms of fire rated protection. There's nothing else that gets one-sided protection. Certainly nothing inside the building that's related to any of these fire rated duct applications. That should look like this, where the entire assembly is properly symmetry tested and performing for all fire exposures on either side. That's what's in the code. That's what needs to be done. And our fire rated duct systems need to be equivalent to that. And that means, quick recap, we need to vet out and eliminate the ones that are not tested for symmetry compliance. Duct A has no legitimate use in the code. We need to eliminate those that are in the wrong orientation. They have no continuity to their design. They have not supported correctly for the orientation. And we need to use them the way that they were tested. If it was cantilevered, we need to make sure it's cantilevered and supported on at least one side. Is it suspended? There's no such thing in drywall land. If it's a duct system, it's going to be suspended, and we need to very carefully, because of that, follow the hanging system requirements. Remember, there is no gripple wire and strap in fire duct land. If you don't believe these things that I tell you, I encourage you to go to the Gypsum Association's frequently asked questions, and you're going to see that they say the same thing. And for your architectural friends who might say 721.1 allows me to build things out of drywall, I advise you to look at the top of that table. It says partitions. That means vertical orientation. You do not get to put those in the horizontal orientation. 722, the finished table says the same thing. And you'll notice in both of these cases, the paragraph that describes the use of the table talks about non-symmetrical assemblies. We're talking about the ability to test both sides. You don't get it to put it all on one side. And if you think it's just those tables that say that, if you go to the Gypsum Association's design guide, it says the same things. All of the known drywall designs have these limitations. All of the performance tables in the building code say the same thing. And so that's our benchmark for fire rated duct systems. And when you see a fire rated duct system, there's lots of reasons they may have done it, not just to get to that fire resistance. So not just to get to that equivalent fire resistance. Very, very often we're using fire rated duct systems for economy, speed, schedule, and those are all good things. We want a building that can go up quickly. We want one that can go in cost effectively. But when we do that, we need to pay attention to the fact that, okay, I can skip 2 out of 5 inspections if I use the fire rated duct system. But if I do, am I going to pass those inspections because I've done it correctly, that I've used the correct product? That's the question. That's the question. Because we can't do it after the fact. We need to know it up front, because we know that SMACNA minimum, hanging systems, anchors, joining methods, and duct construction do not get us to fire duct land. We're going to look at some listing cards and find that there's none of them that have an underlying backbone like that. And the skin matters no more than the ability of the skeleton to hold it up. So it's going to be rigid trapeze supports. It's going to be SMACNA on steroids. It's going to be very, very robust. And we may or may not need insulation value. We're going to focus on that in the next session, because all of these paths land at the point where we do need to test both sides and use the lower of the two results. But all of these paths do not require the same temperature control. And we're going to talk about why that matters. And I don't care whether it's in the first paragraph, stairwell pressurization, the second paragraph references elevator shaft pressurizations, shaft replacement in the second bullet, all of the performance protection described in the third bullet, observing the fact that fan enclosures, power, and control wiring may be implicated, because they all land at 703.2.1, where we must do the fire resistance exposure on both sides of non-symmetrical assemblies and use the lower of the two results. And we find that all of those same concepts come from all of our NFPA references, the continuity, the symmetry, and it's been like that forever. Since the inception of the International Code Council, every jurisdiction that's ever amended that has never, to my knowledge, anywhere across the United States, amended the fundamentals of fire resistance that we're talking about. And the same goes for all of the NFPA references. These are the basics of fire resistance. And I give you these full citations so that if you ever need to circle back and read it for yourself, you have that for your future use. At this point, we would take questions. In the absence of questions for the online delivery format, I'm going to ask you some questions. So I'd like to know what you think about question 1. Based on what we've talked about, are all systems tested under pressure? Question 2, are we supporting all fire rated construction with equal or greater fire resistance. What do we call that? Question 3, continuity applies to vertical fire resistance only. We don't need to worry about it when it comes to horizontal fire resistance. And then finally, question 4, can gypsum wallboard enclosures be suspended or cantilevered beneath an interior horizontal duct? That needs to be fire rated.